Hey everyone, Katrina here, and today I'm going to tell you all you need to know about special triangles and why they're so important in trig. Be sure to subscribe for more of these videos so you can learn even more. Okay, let's dive in. So special triangles are the core of trigonometry, and they help us determine the exact solution for so many trig problems. And that's really great for us because then we don't rely on approximate answers, and it also helps us solve everything a lot faster. So let's go ahead and dive into the two main types of special triangles that we have in trigonometry. And make sure that you memorize these because they will definitely help you on your exam. So special triangles are always going to be right angle triangles. So they always have one corner that is 90 degrees or pi over 2 radians. So for this video, I'll show you the special triangles in both degrees and in radians. Okay, so we will start with radians and then we will also show it in degrees. Okay, so this first triangle that I'm going to show you is, we call this in degrees, you'd say the 30, 60, 90 triangle, or you'd call it the 3 pi over 6 in radians. So in this case, let's do that one first. So if this, like we said, is 90 degrees or pi over 2, let's say that this angle over here is pi over 3, this angle over here is pi over 6. Opposite from pi over 6, you have a side length of 1. Opposite from pi over 3, you have root 3, which is nice to remember. And opposite from the right angle, we have a length of 2. Okay, and now let's copy again this triangle and show it in degrees. Please note that these triangles are not drawn to scale. Okay, so if we do the same one in degrees, we have that this over here is 60 degrees, 30 degrees, across from 30 you have 1, across from 60 you have root 3, and across from right angle you have 2. Also, you can definitely check out my previous video where I talk about converting from radians to degrees if you want to see the actual process, how to do that. It's really quick. If you go from degrees to radians, you do degrees times 1 times pi over 180, and that will give you your answer in radians. And if you want to go the other way, you do radians times 180 over pi, and that will give you your answer in degrees. So this is just a little aside how to convert back and forth between degrees and radians. Okay, so let's call this special triangle number 1, and now let's go and do our special triangle number 2. Okay, so this one is an isosceles triangle, so I will do my best to draw this to scale. So that means that this length and these two side lengths that I indicated are of equal length. So let's draw that once more over here. Okay, so again, these ones are equal length, and we have a right angle triangle. So these are our 1, 1, root 2 triangles, meaning that these two ones of equal length both have a side length of 1. Our hypotenuse has a length of root 2, which you can also find using Pythagoras theorem. And then we can actually derive this triangle because we know the total internal angle of a triangle is 180 degrees or pi radians. And if this is 90 or pi over 2, then these two over here must be 45 degrees or each pi over 4. So we have pi over 4, and pi over 2. And in degrees, that would be 45, 45 degrees, and then your 1, 1, root 2 in terms of your side length. So make sure that you have these memorized. Anytime you see radians such as pi over 6, pi over 3, pi over 4, or degrees like 30, 60, or 45, that should be a dead giveaway that you have a special triangle, and then you can apply these side lengths. Also note that you can have similar triangles where you can multiply your whole triangle by a factor, and you can still have special triangles in those cases. So you can grow them. So the angle will stay the same, but for example, you can grow each of these by 2. So you could have, for example, 2 root 2, 2 and 2, and that would still be a special triangle because you're preserving the angle you're just scaling it by a value of 2, for example. So that's just good to know that you don't have to have these specific side lengths. You can have a multiple of these side lengths so long as you preserve these specific ratios and the relationship between, if you preserve these specific angles and the relationship between these angles and these side lengths. Okay, so let's go do a little example to show how we can use special triangles and also how to recognize special triangles. So in this case, we're going to want to find the exact value of, what do we want? Sine pi over 4. So what does that equal? So you could right away go ahead, plug this into your calculator, but that's not what we want to do. We want to rely on our special triangles and we want to put that calculator away. Okay, so pi over 4 is our angle. So this is our theta. When we draw out our unit circle, we always want to put our theta in these angles. So the ones that are hugging, I guess you can call the origin of our unit circle. So our theta that we're considering, I'll highlight in yellow, would be these ones over here. So we're looking kind of at that theta, the bottom one. Okay, so we see that it is pi over 4. We also want to figure out which quadrant does this fall under. So if we go through our angles, we know we go from 0 to pi over 2 to pi to 3 pi over 2 back to 2 pi. So again, what quadrant does pi over 4 fall under? Well, we can see that that falls under quadrant 1, so we can draw our triangle right over here. Always draw your right angle triangle. And this is our angle, pi over 4, so we're doing that hugging the origin, and we have that as pi over 4. Just for reference, we can fill in our other angle, and we know that this would also have to be pi over 4 because we recognize this as a special triangle, and we also know that the total internal angle within this triangle has to be 180 degrees or pi radians. So following process of elimination, this last one also has to be pi over 4. Okay, let's consult our special triangles. We see that this is special triangle number 2, so it has side lengths 1, 1, and root 2. So that means we can fill those in. So we have 1, 1, and root 2. Okay, so again, we've filled out our triangle, but how can we solve for this value over here? This is where you have to remember the side length ratios of our trig ratios. I have a video that goes over this in detail, so definitely check out that one as well. For the sake of this video, I'll let you know. So sine theta has a ratio of y over r, which you can also think of it as your opposite over hypotenuse. Y is our vertical and r is our radius. So in this case, what do we see? Our y value is 1 over here, and our radius or hypotenuse value is our root 2. So let's just go ahead and fill that in. So that means that sine pi over 4 is going to equal to y over r, which equals to 1 over root 2. So there we have it. We were able to solve the exact answer. Sometimes your teacher doesn't like it when you have a root on the bottom, so you might have to actually go ahead and rationalize this. All of this means is that you just multiply your denominator and your numerator by your square root. So this gives you root 2 over 2, which is equivalent to 1 over root 2, but now you no longer have a radical on your denominator, and that is your final answer. If you enjoyed this video, please drop a like and comment any questions that you have. I'll have more videos on trig coming your way, so be sure to stay tuned and subscribe for more. See you next time.